Hello, all. Welcome to our final seminar in the fall seminar series. I'm really very happy to introduce to you Professor Laura Dalton. She's an assistant professor in civil and environmental engineering at Duke University. Uh, she joined Duke in August 2022 after obtaining a PhD from North Carolina State University. She's an experimentalist, and her research interests include understanding and manipulating chemical and physical processes that occur during transport in both engineered, and natural porous geomaterials, the cementitious and geological materials as examples. To this end, she uses quantitative tomography to obtain complementary information to better understand complex processes for permanent CCUS solutions in the built environment. Thank you very much, Professor Dalton, for giving us this talk, the title of which is Studying Carbon Capture, Utilization, and Storage in Geomaterials Using 4D Tomography. Thank you. All yours.
All right. Thank you very much. It's a pleasure to be giving this talk today, and I appreciate everyone being here. Sorry, I have a little bit of nasal congestion going on, but we'll make it through this. All right. So I will be talking about studying carbon capture, utilization, and storage in geomaterials using 4D tomography. And just to start off, a little bit about me. So I actually obtained my first degree in graphic design way back in 2012. Sorry, it's a long story, but then I entered into civil and environmental engineering. I had thought I wanted to be an architect, and then I just realized after the degree that engineering was what was right for me. And during that time, I got to work on some foam cement materials. That's the image you're seeing here at a local national lab in Morgantown, West Virginia, which is close to where I'm from. Then I spent about a year doing a master's degree on asphalt concrete, but quickly realized that just wasn't what I wanted to do long term. So I went back to the local national lab and started working on carbon capture and storage and saline aquifers. So how we store CO2 deep below the ground. And then from there decided I want to do my PhD and kind of combining cement and supercritical CO2 and how they react together. And then got to do a Fulbright in Finland. And then that has led to me being an assistant professor at Duke, which is where I am at now. But so most of the motivation for what I do stems around carbon capture and storage wells. So there are millions of these wells throughout the United States and the world. But so these are wells that we've used to extract some type of material from the ground, such as petroleum, natural gas, and then we'll come in and we'll actually use it to store CO2 permanently. But in reality, now that this has been studied for at least 30 years, we've been able to actually take cores out from the ground and from these wells, and we're seeing that CO2 is actually leaking back into them to some extent. And so I'm really interested in the service life of these structures. But so they're made with foam cement, some of them offshore and on the wells. Right, we'll store CO2 in the ground, and that's really what these images are depicting. We'll plug these wells, but in reality, to some extent, we can have some leakage back into these structures, which could compromise the structural service life, especially when you have supercritical CO2, because it's a whole different beast when you transition from gas liquid to supercritical CO2, and we'll talk about that more. And quickly, this is kind of an overview of everything I've worked on and kind of where I'm going. So CO2 transport and storage in geological materials, Portland cement-based materials, some quantitative imaging development, so looking at different photographic techniques. And then I've done mostly just supportive work and some composite material development that I'll touch on. And the broader impacts are really carbon capture, utilization, and storage in porous materials. So it's for the built environment, but also in deep saline aquifers. So, and carbonation connect, right? It's all interrelated to really just how can we put CO2 out of the atmosphere and permanently store it through mineralization as calcium carbonate back in these geomaterials. And we're really trying to look at, can we systematically design carbon capture and storage in materials or to promote it over time type of thing. So that's really what my group is working on. And so I wasn't sure about everyone's background, so we'll do a little bit on cement chemistry just to get everyone up to speed. So to make cement, you basically need lime, silica, alumina, and ferric oxide. So another way to think about it is Lisa, because iron, anyways, but what you really need, right, 63% by weight of lime, which is calcium oxide, and then around 22% silica. So those are like the primary ingredients. And then we'll heat these very high to get to the point that we have clinker, which we grind with gypsum to control our hydration and setting properties. We don't need to really get into that. But so from there, you basically have these two materials, A-light and B-light, which make up 75% of your cement material. That would be in a bag that's then shipped and used, or what you've maybe seen at Lowe's, just like one of those bags of cement. And that is this powder that I'm showing here on the right. And so just a quick background on hydration. So the main components are A-light and B-light. And then these contribute to our hydration products when we add water. So you'll start having this reaction of hydration, and we get calcium silicate hydrate, which is the primary binding material that binds all the aggregate together in concrete. And then calcium hydroxide is the secondary component that's technically less stable than calcium silicate hydrate. But so again, just some terminology. So paste, so cement paste is cement and water, and of course air. So to some extent you have air as a porous system. Mortar just means you've added fine aggregate. And then concrete is when you have coarse aggregate and fine aggregate. And once it's hydrated, or really as it starts hydrating, any of the materials, paste, mortar, concrete, you have this really complex pore system ranging from nano to micro, sometimes into millimeter scale pores. So it's a very, very complex pore system. And then just to mention, water to cement ratio is an important topic. So just wanted to mention that it's basically the weight, right, of your water over your cement. But if you have a higher water to cement ratio, you have inherently have more porosity than a lower water to cement ratio. So just wanted to touch on that briefly. And so, at least for this talk, the three tomographic techniques I'll be talking about are X-ray computed tomography, or X-ray CT. I'm going to talk about dual neutron and X-ray tomography. And this system is located at NIST in Gaithersburg, Maryland. But it's basically two beams perpendicular to one another, so you can get complementary information. And then electrical capacitance tomography. And really the reason for this is that there are trade-offs depending on what you're trying to study or see when you're running an experiment. And so each one of these techniques provides slightly different information, and how it goes from 3D to 4D is just that you're scanning something in 3D over time, and that's that fourth dimension. But based on high spatial or temporal resolution, if you're wanting to see something very, very fast, like electrical tomography is very effective at that. Whereas X-ray and neutron are slightly, they take much more time, usually. However, there are new systems. But for most of this talk, we'll talk about X-ray computed tomography. So I imagine many of you have, or at least have seen or had an X-ray at some point of a bone. This is actually my bone post-surgery. So you can see, I don't know if I can highlight this really quickly. I now have a nice little metal piece of metal in my knee and this cool biocomposite screw. It's just fascinating. But anyway, so X-ray CT, fundamentally, this is an X-ray radiograph. So just like you would scan a bone, for tomography, what you're doing is you're taking a scan, but basically your stage is rotating with your sample. So every angle, you're getting one of these radiographs. And then you can take those radiographs and basically reconstruct them into a 3D volume that's made up of these image slices. So that's how you get your 3D data. And then again, 4D data just means you're doing this over time. And really quickly, for geomaterials we'll talk about today, I just wanted to kind of give an overview of what these different what it would look like under or after you've scanned the material. So for foam cement, so very porous cement, so we have unhydrated cement are these brightest particles because it's all based really on density. So your higher attenuating materials, so the brighter ones are higher density materials in your, in this case, composite materials or geomaterials. And then these darker areas are pores, which are filled with gases. So gases, in this case, mostly air, very low density, so they show up very dark. And then, yeah, so we have large pores, and then hydrated cement is everything that's in here. For mortar, the sand is right here. And we can really only tell that because of the sharp edges, because the density is actually very close to that of our binding material in the middle. And just to mention, so gel and capillary pores, those nanometer scale pores, we cannot see those with X-ray CT, but there are other ways to study that as complementary information. And then this is a sandstone on the right, and this is supercritical CO2, and then the rest of the pore space is filled with a brine salt water to simulate what's happening underground. So just wanted to kind of orient everyone to what you're looking at for these. So really the first thing I worked on ever with X-ray CT scanning was to quantify the evolution of pore size distributions. And so I'm going to talk about that first. So foam cement, I mentioned briefly earlier. So it's used to make these, to basically stabilize the well casing for petroleum wells, and then eventually carbon capture and storage when we store the CO2. So these are usually made with 15 to 30% entrained nitrogen. So that's extremely porous compared to our regular concrete that we use for above ground infrastructure. And the reason for that is because in the subsurface, you have some movement. So you don't want your structure to be quite as rigid as we do usually in above ground. So anyways, but you're still using, it's basically Portland cement. They just have slightly different names, Class G, Class H, or some common ones. But the traditional way of studying this was with this blender. So you would just make these in a blender. But in reality, in the field, as you're generating these materials, it's changing pressure as you're going down and pumping it below ground. And so only studying at atmospheric conditions was kind of a problem. And so this foam cement generator was developed by Derazier way back in 1991. But we were just studying, we made one and we studied this. So basically we wanted to compare these three different foam cement. So this is the blender cement. So that was made in the blender. Foam cement generator. So the pores are much smaller compared to the blender and kind of better separated. And then field, of course, you have a lot more variability in the field. But so this was one thing that was studied, was just how we should be doing laboratory experiments to really replicate what's happening in the field. And so here's another example just of different qualities. So quality really just means you have more porosity. So you've entrained more nitrogen in your cement slurry when it was generated. And so you can just see like there's an increase. I've just segmented out all of these pores in 3D. And so 20%, 25 to 40%, you can just see that the bubbles are getting larger and they're not as well distributed. And we can segment this out using image processing. So basically, there are many workflows from ImageJ, there's Pergeo, Aviso, Dragonfly, many really great softwares out there that are open source or commercialized. This happens to be in Aviso, but so we can segment out pores and then kind of characterize the porosity based on different sizes. We can segment out and really characterize what's going on with time. And so how we did this was we just scanned, we made some cement slurry with nitrogen. This is blender. And then we just scanned every 20 minutes for 9 scans. And then a couple of days later at the end, after the foam cement had hardened. And then I was tasked with separating out the pores, characterizing them, and just seeing how they're changing with time. And one thing you can see here with the blender foam cement is there's a lot of variability with size. shape of the bubbles, it's very different than if you go to the at least the early stages of the foam cement generator curing evolution. So again, with time, just looked at 20, 40, 60, 80, so on. And just looked at how the bubble generation and evolution changed with time as it cured. And so how could we get useful information out of this? So since I was able to segment out those bubble volumes, we could then plot those, do a comparison, basically showing that the bubbles are less uniform with the blender method than FCG. And then also we studied sphericity, which just means the point to which the pores are spherical, which basically can then be tied to strain evolution on the bubbles. So anyways, just wanted to share like some ideas of how 4D tomography can be used. But this was my first experience dealing with X-ray computed tomography. It was a very interesting project. So the next thing I'll just touch on briefly is, so I talked about CO2, right, carbon capture, storage, and utilization. So something we were studying was how can we quantify in the subsurface, you have brine in the geological material. And so that can also be intermixed with CO2 if it's leaking. So we were looking at what happens when we just basically soak these different foam cements in CO2 saturated brine for a month, 6 months, a year, so on. And then how does the material degrade? And so what we were able to do here, so this is just a regular cement paste. This is a 10% quality cement or foam cement, and then a 20%, 30%. And so what we can clearly see is like as it was submerged in this salt, CO2 saturated salt solution, basically, it was penetrating into the sample radially from outwards inwards. And so we could quantify just how far that happened and just start to characterize how quickly this material could degrade under these conditions. So that was something I worked on for a little bit. But the bigger thing was studying CO2 storage in saline reservoirs. So, and something I was interested in is if we could increase CO2 storage in the subsurface if you do multiple cycles of CO2 injection. So to do that, I learned how to run this system here on the left, and this is at NETL in Morgantown, West Virginia. So we have a confining pump in the back, so to put confining pressure on your sample. And then we have an injection and receiving, so sending, receiving fluid pumps that are then interconnected into our X-ray CT device. And so we can get high temperature, high pressure, and once we're there, that's, so to get to supercritical conditions, it's above 31 C and then like 1100 PSI. And we can far exceed that with the system. But so what we do is we initially saturate the system with brine. So this is, again, a sandstone, because that's what the initial state of the system would be, is brine. And then drainage, so we inject CO2, and then we bring brine and do another injection. Because basically how it works is we store CO2, and the salt water that was displaced will eventually come and kind of run through the CO2 and help break it up. In theory, that's what's supposed to happen. But so I just did a second cycle to see if we actually could increase the amount of CO2 that was stored. So this was a study that I did probably like 5 years ago. And I looked at 2 sandstones. So one that is very porous, large pores, very well interconnected. So this is Bentheimer, is just the name of the sandstone. And this is the first cycle and the second cycle. And then Nugget was another formation, which had more variability in its porosity. So some large pores, but then very small porosity here and there, and not as well interconnected. And what I found was by doing, right, and one, you can see the porosity, so like 25% and 11%, so much higher in the Bentheimer. the one thing that I saw or realized from this is that going from one cycle, so we had like a 6.4% saturation, here only about 2%. And this is just in the pore space, quantifying it based on the pore space filled with CO2. We had an increase to 16.5% for the Ventimer, and then up to 12.4% for the nugget, which was pretty substantial. It's actually more substantial for this tighter nugget sandstone. So that was one thing that we were able to characterize. And then also looking at the spherical diameter and trying to understand what effect that's having. But anyway, so from this tomographic data, we can also then start to characterize the porosity, your grains, and then how the supercritical CO2 is stored and if that's having an effect on immobilizing it, because in reality, we want it immobilized so that it's sequestered, it stays in the pores, and then will slowly mineralize over time. And then another thing was the strain evolution and contact angle. So contact angle and contact surface just means the point where your solid, liquid, and in this case, supercritical CO2 all connect. And I was just able to characterize how, what effect it had on this single supercritical CO2 little blob that was in the porosity and how it evolved as we did that second cyclic injection. The takeaway was it did improve the amount that could be stored and actually improved more so for the tighter porosity sample. And then just really briefly, another option is just doing like pre and post scans. So you scan something before you do something to it and then afterwards. So in this case, we were looking at, this is for 6 months, each of these samples. So this sandstone and this limestone were placed in an autoclave with CO2 saturated brine for 6 months. So this was before and this was after. And with this limestone sample, what we're seeing is dissolution. So we're actually seeing porosity developing with time as it's basically just engulfed or submerged, I mean, in the CO2 saturated brine for 6 months at these really high temperature and pressure conditions. Whereas for the sandstone, we see that there's a pore here that is actually closed over that 6 months. So that's precipitation. And so it's really just showing another way you can study something with tomography. So pre-post scanning, but it's very variable, right? Because technically these were subjected to the exact same conditions, but here in this limestone, we see dissolution. In the sandstone, we see precipitation. So anyways, complex topic to try to characterize exactly how different formations will behave, because you can also have both in some cases too. I've seen that in different formations. So I mentioned that then I started my PhD in 2018. And really what led me to do that, I wanted to study more, well, have some freedom to study some more things that I was interested in. And having the background with foam cement and now supercritical CO2, I could combine those. And what I wanted to start studying is really this reactive transport of CO2 in Portland cement-based materials. And since I knew how to run this X-ray CT scanner and high temperature, high pressure system, this gave me an opportunity to do that during the PhD. So some background, more background on cement. So I mentioned it has this really complex pore system. And what you're seeing here on the y-axis is degree of saturation, and on the x-axis is the square root of time. And if you have a piece of mortar, concrete, etc., it's just like a sponge. If you put it in contact with water, it will start to, basically through capillary action, it will be absorbed into the material. And so many studies have been done on this, but we have an initial sorptivity and a secondary sorptivity, which means your really small pores, those ones I said we couldn't see using X-ray technology, X-ray CT technology at this time, at least. Those will fill first, and only after those have filled, your larger pores should begin to fill with water. And so to study this, I was really interested in, well, what if you have something like CO2 in your pore system and not air? because we actually put air in concrete on purpose to help with freeze thaw and to slow down the ingress of water into our above ground infrastructure. But I was very curious, right, in these subsurface conditions where we have CO2, methane, right, interacting, how could this affect the rate of water absorption in a cement-based material, especially given CO2 has a much higher solubility, right, orders of magnitude higher compared to air or nitrogen. And so that's really what I decided to study. And I knew that we could see those large pores really easily because having the experience with loam cement, you do have to use a very small sample size for the system. So just to put that in context, that's tiny, so that you can see what you're trying to see. But so I made these really porous samples and then purged them, one with CO2, one with methane, one with nitrogen, and then brought water in contact with the sample and started CT scanning to see what would happen. Well, oh, and I'll walk through like what this looks like from an experimental standpoint, because I am an experimentalist, so I like to share some of the details that are sometimes overlooked if you don't do experimental work. So here we have our source, our detectors over here in the system, and this is our pressure vessel and our sample. This is mortar. It's right here in the middle. This is aluminum sleeve holding it together with that confining pressure. And then I have a Teflon spacer, and we'll touch on why I needed to do that in just a moment. So we did the gas purge, and I just want you to kind of pay attention to this area right here, which is much lighter. So we injected CO2 for 24 hours, and same with methane and nitrogen for other samples, and then came in the next day and very carefully injected water into this little spacer below the sample until it came in contact, and then we immediately stopped so that we could start seeing and imaging what was happening. It took 3 people to make this work. But so I did that for 24 hours, 30-minute scans, and here's one of the samples. And again, like we mentioned, low density, high density materials. So initially this pore was filled with CO2, and then we can see this slightly higher density material coming into that large pore, and that's what the water was, or it indicates that water was advancing into that large pore. And so I did this for the CO2, methane, and nitrogen. So CO2 is in red, methane's in yellow, and nitrogen is in green. And what I want you to focus on is this change to blue over time. So this is within the first 30 minutes. Water had already moved into the CO2 filled sample, but nothing happened in methane or nitrogen. And this is even into 1 hour, and we get into 6 hours here shortly. It's going to keep rotating. It's just the same sample rotating with time. So we're at 2 hours. Still nothing has happened in nitrogen or methane, but we see that water advancing into CO2 more and more. And actually we get to a point around 6 hours, I think it was 6 hours, where it's just completely saturated the CO2 sample. Yeah, there we go. And then it isn't until around 12 hours that I saw a change in methane. And even during that whole 24-hour period, really didn't see a change in nitrogen. So we can move on. But so what useful information can we also get about this or from this tomographic data? So I mentioned this plot earlier. We covered that. So I can make these plots. I'm really just focused on the secondary sorptivity because that's what I'm seeing in the large pores. And I can just take, here's the pore space, here's the pore space filled with water, and then I can make that part of the curve using those data points for each material or each gas that was used. And so something, well, one, okay, so right, CO2 was much faster than methane, and methane was faster than nitrogen, so in line with the solubility of these materials. But then something we didn't expect was this bilinear or this nonlinear behavior, which what we think is happening is once you get to that point, the calcium hydroxide is reacting to form calcium carbonate. And then as it reacts, we return back to this linear progression. So this was just something we hadn't expected, and that was pretty interesting that we saw from this experiment. And then from there, we were able to make just this small sorption model, very basic, just explaining what we believe is happening based on what I just mentioned with the CO2. So basically you have calcium hydroxide, which is the least stable of calcium hydroxide and calcium silicate hydrate. We purge the system, we bring water in contact, it starts to react, the initial sorption process. So that first part of that bilinear plot. And we have this transition point where CO2 is coming, or where water is advancing and reacting and forming calcium carbonate, but the internal pressure in this pore is greater than the capillary effect. At least this is what we believe is happening. And then it really transitions to this more diffusion controlled process into the larger pores. So that was one part. And then I started wondering, again, because I'm more interested in supercritical CO2 and what effect that's happening as opposed to gas CO2. So what if we flip the scenario where we have, now instead of purged with a certain gas, we have different degrees of saturation in our sample is really what I was interested in. But also then it's exposed to different states, so gas, liquid, or supercritical CO2. And this is just a phase diagram for CO2, and just at different pressures and temperatures, you'll have a different CO2 state. And I wanted to know what happened like the second CO2 came in contact with a Portland cement-based material to really understand how the reactive transport would affect the calcium carbonate carbonation front. So again, same system. Wanted to look at mortar again because I knew porous mortar would work well for this. And then basically as dry as we could go without cracking our samples, around 50% and 100%. So that just means as dry as we could get it, so the pore space barely had any water in it, then 50% saturated, 100%. And then exposed each one of those samples to gas, liquid, and supercritical CO2. And this will walk through the CO2. So we have our system, we have our sample in there, it's closed. We've done our best to not expose it to any CO2 up to this point. We have it under nitrogen. So the second it comes in contact with the sample, the CO2, came in the next day, opened up the valve, exposed it. We could do sequential scanning and see how that CO2 is moving through samples with different amounts of water in them, and then do a post scan. That's just a higher resolution. And so how can you characterize this? You have a before and after, or in the case of the dynamic, 1, 2, 3. So we can see this change in the histogram of our image. So it's gone up and over, and that's indicating that there has been an increase in a higher density material. In this case, which could be confirmed with other methods, is calcium carbonate. So for gas CO2, didn't really see anything when we have basically a dry system, which I expected. You don't have a high concentration, as high of a concentration of CO2 with gas. Whereas liquid, it was very slow, very much looks like diffusion, just kind of moving up gradually. And then supercritical CO2, whatever moisture was there, it reacted with rapidly and then just kind of fizzled out, which was really interesting. And then for 50% degree of saturation, we observed that the gas was actually very stable and reacted pretty uniformly and carbonated within the first hour, whereas liquid, same thing, but in an unstable manner, because we see this flow to the left, and same with the supercritical CO2. But so it was much faster chemical reactions that we were able to observe with the 50% degree of saturation compared to the 0. And just want to touch on thermogravimetric analysis. So how can I confirm that what I'm seeing, that change in density is calcium carbonate by using thermogravimetric analysis. So we know between certain temperatures, calcium hydroxide will will decompose. And so we can calculate that, and then also calcium carbonate. And then you basically just use stoichiometry and characterize what's going on. Main takeaway, again, just that gas CO2 sample. If you look at it as CO2 sequestered per gram of cement, it sequestered the most. So that also confirmed the observations, and so on. There was actually, well, more than half less, I guess, in the gas CO2 sample. But so there was some reaction in that first gas sample, but we couldn't see it. So again, just a limitation of the method. And then we could quantify some high density materials and how that was changing when the state of the CO2 changed. Then another additional method you can use is sorption analysis, which just can tell us more about that small pore system we can't see with X-ray CT. And it's just a step-by-step process where you can say, okay, this pore size is emptying at certain relative humidities. And so you can characterize that small pore system with some understanding of where that calcium carbonate was depositing and what effect it had on the pore system at the time. So the 0%, 50% were going down. The 100% was a little more, it seems like there was precipitation and dissolution happening to some extent in that sample, or those samples. But this is just a way to do some complementary quantification of data to further confirm what you're observing with X-ray CT. So we already talked about this. Well, I'll show the video. This is just to show the timing. And again, just that the 50%, there's clearly something slightly different going on compared to 0%. So the first thing I've had my postdoc do is actually take that data, and he's developing a model, running a linear stability analysis using the reaction rates we have, because when we run these experiments, we also have LabVIEW data that's monitoring the pumps that we're using to flow through the system. So we can use all this and calculate reaction rates. I'm not going to get too much into this, but he's very much the model expert, and he's working on this for right now. But he's had very good agreement with our results so far. So, and basically you have this larger, what it is interfacial area between the CO2 that's entering the system and then the amount of water that's already in the system. And as that changes, we're able to really make sense of what we were observing. But this is still a work in progress. And this is just showing that some feedback mechanisms based on where you're at with degree of saturation and what effect that will have on how stable the advancement of your carbonation front will be. But again, work in progress. Oh, and I'll just touch on this. This is a colleague from my PhD who was studying putting calcium carbonate in wood. And it was just a really fun project to do with CT, because if you have high contrast and density of materials in your system that you're scanning, you can really get some nice images. So the very bright materials are calcium carbonate, and then we have our pores, and then the lighter material is the wood structure. So this is pine, this is a beech material. And so, well, and he pressed it because we weren't getting composite action. So it's a composite material, but we didn't have any composite action. So we were pressing it and then studying that and what effect that had on the material and mechanical properties of the material. But anyways, this was just a really fun project I got to support and wanted to mention it as well. A slightly different building material than Portland cement. So we talked about X-ray a lot, and now I'm going to transition into a dual tomography experiment that I did. So the trade-off is neutrons are really good at capturing changes with water, whereas X-ray is better at changes in density, meaning like the structural content of your material is better captured usually with X-ray CT, whereas neutron can really capture the flow of water really effectively. This is not with CO2 because it was a first experiment, more of a proof of concept. But I'm going to share these results. But the next step is really to study CO2 and reactive transport, hopefully one day. And the reason we were studying this was for the interfacial transition zone. So again, the interfacial transition zone is the slightly more porous region right by your aggregate. It's been a little controversial in the literature, but still I would say it's pretty well supported. But we wanted to study this in some way, and we thought if we put a single aggregate in our sample, in theory, as the water goes down, it should go to that porous region first. So we wanted to study that. And so slightly larger sample, that's just a matter of what their system can do compared to some systems I've used in the past. You have the sample in there, neutrons going one way and X-rays going the other, and you get both sets of data continuously as you're doing 4D experiments. And what we got here, it just really helped with phase segmentation, just having both neutron and X-ray. So that was one aspect of it that really was enhanced just from having that complementary data. And then here's the progression with time. So if you look at the X-ray, we don't actually see any change with water, but we, even at the top here, but you very clearly see this change to brighter material, which in this case for neutron is the advancement of water because it's a different method, neutron tomography. And now we're going to zoom in on some results. So basically I can see this visually, right? But then using image processing, I can segment out this change and characterize how the water is progressing. So this was, okay, so we're going to zoom in on this little area just so you're not too confused. So this is that single aggregate, and then the colors I'm showing are the advancement of water. So that's 1 hour, 2 hours, 3 hours, so on. Great. And then that's combined. Then I also did image subtraction. So this is taking image 2, subtracting out image 1, and then this is the difference with time and how that changed. And we do see this little bit of a gap here developing, which I'll touch on later. But even if we cut into the material, we're not seeing like this preferential pathway. When we were actually trying to study ITZ, like in that context. But we did see that the water was kind of avoiding that space in a way, which I think I've thought about this a lot. And I wonder if it comes back to the fact that it's more porous, there's more air, which in theory would actually delay the advancement of water to that point under like capillary effect conditions. If you're flowing through something, of course, and it's interconnected, that should increase the percolation of the water. But anyways, that's one thing that we studied. And then here's a second sample showing very similar results. But the main takeaway here was that there's still a lot of room for improvement to study these interfaces and complex transport with this system, because really the resolution was around 60 microns, which if you've read anything about ITZ, it's probably sub-resolution, right? So there's still room for improvement, but this was a first step just to study if we could even see the water and how we could reconstruct the data. And it was published last year. And so lastly, I'll talk about electrical tomography. So I had experience now with X-ray predominantly, and now a little bit with neutron. And my advisor at NC State, his expertise was in electrical tomography. And that was something I knew nothing about. And he encouraged me to apply for a Fulbright, and I was very fortunate to obtain that opportunity and go to Finland and learn from some of the leading experts on this topic. But just like I mentioned before, we were looking at this transport of CO2, or sorry, of water in our system with X-ray and neutron, but there were clearly some limitations. So we wanted to now study in the context of electrical capacitance tomography and really push the temporal resolution because up to now, just for the experiments I've done, it was mostly around 30 minutes to an hour, and then resolution in the micron area. Whereas electrical tomography, the trade-off here is you can get down to seconds, really even milliseconds eventually. And then, but your spatial resolution is much lower. So like you can't see as much detail, but you can see change very quickly. So it's a different technique. It's a diffusive measurement technique where you have a grid of electrodes. And kind of the other benefits of this method are, right, so fast, relatively inexpensive compared to other tomography systems, pretty safe because you're not dealing with radiation, and then much larger sample size. And in theory, this could be portable, right, as this technology advances. So it'd be great to be able to take this out and like actually study something out in the field and look at transport of like a cracked column, for example, something like that. But so the three research questions we were trying to study is, can we actually detect the water path around an aggregate? And then can we, with different crack patterns, will it actually be able to crack those? So some spatial resolution, to what extent can we capture different crack patterns? And then temporal, the biggest part of this was really how fast can we see this transport? So made some samples, shipped them to Finland, about 200 pounds of concrete samples. And then there, so this is the grid that wraps around your sample, and then it's connected to this excitation device. And then after you have your data, you can reconstruct it and then make sense of what's going on. And it's all based on permittivity. I'm not going to get too much into that. But and we use absolute imaging. Anyways, okay. Details that probably aren't too important. So as the water, so basically we just put a reservoir on top of our sample and then ran, well, we did a dry scan. So scan, in this case, you're doing a measurement as a baseline. So that's what's shown in blue here. And then as the water's going down, each one of these electrodes will go through very quickly and do measurements to each other. One. So basically you ground one. In this case, I'm just using 32 for an example. And it'll do a measurement 1, 2, 3. And if you look on the right, you'll see this increase for 24 hours in your electric current. And so that's indicating that you have water making it into your sample. So just wanted to share that as a bit of a visual for how electrical tomography works. And of course you can get other information. So we talked about sorption plots. This is just that first part of the sorption plot, the initial sorptivity. So we can get that just from having images of the water moving down and into the sample. And then we can actually reconstruct our samples. And this took quite a bit of time, but we looked at 2 different water to cement ratios. So this is a lower water to cement ratio, which means less porosity. And these are just slice images of the results. And then here are the 3D, well, 4D images. So how it was changing with time. And so this is mortar. So we don't see any aggregate, right? It's just slowly advancing, well, relatively quickly advancing down the sample. So yeah, 16.7 seconds was the fastest measurement we got for this sample. And then this is just showing the spatial resolution from turning it. So then I looked at, again, we looked at concrete. So can we actually detect this transport pattern around an aggregate. And we clearly see that right in the middle, we're not seeing any water advance. So we were able to detect that water pathway correctly with this method. And then as for the different crack patterns, this was another sample where we were able, again, no water in the center, but also we have, this was as fast as 0.7 seconds. So very, very quickly, the water moved through the sample because it was quite a big crack. And then also we're even able to detect this very small horizontal crack that I have some images. It's right here, post experiment. So the spatial resolution was enhanced from previous people who have looked at this. So that was a big part of what we were able to achieve with this study. And again, I want to study this in the context of CO2 and carbon capture and storage. But again, for proof of concept, it was just with water to simplify for now. Yeah, so takeaway, we are able to clearly see that there's an aggregate in there and successfully study that. And so really this brings me to what I've been doing for about the past 2 weeks now. So I've been at Duke for a year, but we just got our system. This is a test scan Unitom XL, and it's actually designed for dynamic scanning. We just got training 2 weeks ago, the initial training, and then yesterday and the day before training on our Devon stage that goes in the system that can do tension, compression, and 3 and 4 point bending. And it also heats up to 250 C if you're wanting to study some type of thermal effect on a mechanical property. And this is my group. So Sonia, Kai, and Emma are my 3 PhD students. And this was just after our training. We're slowly but surely learning a lot. These are just some practice scans they've done. This is a piece of coral. This is just a seashell. But it's been fun getting to learn the system and just been really impressed with what the system can do and just how fast it can scan. Like this scan took 15 minutes. This is a geode that I scanned. But again, that's because the system has been carefully designed to increase both your temporal and spatial resolution. Of course, there are always trade-offs, like I've mentioned from all the other slides. But we were able to see, I mentioned for the dual neutron and X-ray scan that we did, we couldn't see the water uptake with the X-rays at all. Or I guess actually the reservoir was on the top. We couldn't see the water moving into the sample. So we actually did a quick test of this with our new system, and we were able to see the uptake of water. If you just set a piece of mortar in water, we could see that changing with time. Of course, we could visually see it, but we could also see it internally. So I was very impressed with this. I did not expect this to be something we could see. And that's just from our practice training. So very excited. Here's an example of the Devon stage that can do tension. It goes in the system. And then here's the deformation just afterwards. But we're really just getting started. But that's a big part of what the past month has looked like for my group. But really just concluding remarks, I just want to say that 4D tomography is a powerful tool. It really just takes creativity and careful planning of what you're wanting to see. And then in the context of transport or a material property changing with time or a mechanical effect with time, like a fracture, for example. Dual tomography provides complementary information, both temporal and spatial improvement, though, at least with that system at NIST for my purposes, we would have to be able to scan a lot faster and all of that and increase the spatial resolution. But you can also, like people have done both electrical tomography and neutron, electrical tomography and X-ray. There's tons of different combinations, again, just based on what you're interested in studying. And future work is really to integrate mechanical properties during reactive CO2 transport to really understand what's happening in the subsurface, and then scanning, but that's going to take some time. Yeah, An ongoing work is really my postdoc working on the numerical models, and then we're just getting started with our system. And here are some references. I have many people to thank. And this is NIST, NETL, NC State, University of Eastern Finland, Aku Sepinen's group, my prior advisor, Dr. Mo Porgaz, and then at NC State, mentor at NETL, Dustin Crandall, and then now TestScan, as we're starting to use our new system. And with that, I'm happy to answer questions. Okay, I did go over, but that's it.